Hello children, hello. Welcome to another chemistry class. In this session, our rapid revision topic is Unit 11, P block elements. Unit 11, P block elements. That is our rapid revision topic in the session. Can we go through? We are discussing the 11th standard topic of P block elements. All of you know what is meant by P block elements. Those elements in the periodic table in which the last electron, differentiating electron, enter into P orbital of valence shell. That is called the P block elements. The last electron entering into P orbital of valence shell. And thereby the electronic configuration comes out to be, the general electronic configuration comes out to be a noble gas core with the NS2, NP1 to 6. This is the area where electronic configuration end up in P block elements, giving NP1, NP2, NP3, NP4 like that. So P orbital, there are three orbitals px, py, pz. NP1, that is group 13 element boron family. NP2, that is group 14 element carbon family. NP3, that is group 15 element nitrogen family. Hope you remember, they got an extra stability for the electronic configuration, half filled electronic stability. Then NP4, that is 16th group oxygen family called chalcogens. And then NP5, the most electronegative element in the periodic table, halogens. And the close filled configuration NP6, that is noble gases. Noble gases excluding helium. Helium cannot be called P block. Of course, it is present along with the P block according to the property with the noble gases. Helium is not a P block element, all of us know, right? Others are helium, neon, argon, krypton, xenon, radon, and the new member organozone. These are the group 18, that is the completely close filled configuration ending up with the P block. While starting with the boron family, boron, aluminium, gallium, indium, thallium, and the member nihonium. Nihonium, that is element 113. That is about the boron family. A detailed talk on boron family we are going to have in this chapter. Next is carbon family, carbon, silicon, germanium, tin, lead, and flerovium. Flerovium. These are the members. 14th group, right? 15th group, nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. Moscovium, right? Then 16th group, oxygen, sulfur, selenium, tellurium, polonium, and livermorium. That is 16th group. 17th group, fluorine, chlorine, bromine, iodine, astatine, and tennessine. These are the members in P block. There are 6 groups. Why 6 group? There are 3 orbitals being filled in P subshell. P subshell 3 orbital, 6 electronic configuration, 6 group, starting from 13 to up to 18. 13th group boron family, also called aluminium family. 14th group carbon family. 15th group nitrogen family called nicogens. 16th group oxygen family called chalcogens. 17th group halogens, and noble gases, inert gases, rare gases, 18th group. Our topic is in the chapter limited to 14th, 13th and 14th group in the 11th standard topic in this video, while the others will continue in the second year topic videos. Okay. So group 13, group 14 in particular, right? So the importance of P block elements, I don't have to tell you. All variety of elements are present in P block. There is metals, there is all non-metals coming in P block. There is semi-metals. Germanium is a semi-metal. Silicon is a semi-metal. Antimony is a semi-metal. So we have semi-metallic metalloid characters are coming in this block of elements. There are metals in the block of elements. There are non-metals in the block of elements. There are gases in this block. There are liquids in this elements in the block. There are solids. Right? So almost all gaseous elements are coming here. All noble gases, fluorine, chlorine, oxygen, nitrogen, gaseous elements are coming here. Liquid elements, the one and only liquid non-metal bromine is here. Right? Solid elements, many solid elements. So the electronic configuration of this group and this group will be NP1 and NP2 respectively. Now whether group 13, 14 or 15, even 16, an important point that we discussed is inert pair effect. Inert pair effect. As you come down, apart from the group oxidation state. See, what is the group oxidation state? The group oxidation state for group 13, it is group number -10. This is the group oxidation state. What about carbon family? Group number -10. This is the group oxidation state. So boron family, group oxidation state, maximum oxidation state +3. Carbon family, group oxidation state, maximum oxidation state +4. Nitrogen family, maximum oxidation state +5. Goes on like that. When you come down the group, apart from the higher oxidation state, a lower oxidation state found to be pretty more stable when you come down the group for heavy members. For example, boron. Boron prefer to give BCl3 +3 state. Aluminium prefer to give AlCl3 +3 state. But as you come down for thallium is not preferring to give TlCl3, rather it prefer to give TlCl +1 state. If you go to carbon, if you come to carbon, you get CCl4 +4 state. If you go to silicon, SiCl4 +4 state. But as you come down for lead is not happy with the PbCl4, rather it is happy with the PbCl2. 2+ is more stable than the group highest oxidation state. This is because of inert pair effect. What is inert pair effect? The valence shell Ns2 electron is not willing to take part in chemical bonding. The valence shell Ns2 electron is not willing to take part in chemical bonding because of the poor shielding effect caused by interior orbitals. If you take up the electronic configuration, for boron, it is 1s2, 2s2, 2p1. This is the configuration for boron. This is the inner shell, noble gas core. If you come to aluminium, it will be 1s2, 2s2, 2p6, 3s2, 3p1. This is the inner core and this is the valence shell configuration for aluminium. But as you come to gallium, you can find there is a difference. There is a noble gas core and you have 3d10, 4s2, 4p1. This is the configuration for gallium. There is a 3d10 configuration coming. And you know d orbitals has got a poor shielding effect. So due to poor shielding effect of 10 electrons in d orbital, the attraction of nucleus over the valence shell will increase. So there will be subsequent property changes. The size will decrease. characteristics will change, which depends mainly on size. And if you come to gallium, then indium. If you come to gallium and then indium, it is quite similar. There is noble gas core 4D10, 5S2, 5P1. See, these two are quite similar. There is a significant difference from aluminium to gallium, because in aluminium and gallium, the fundamental difference is 3D10. While these two will be quite similar, 3D10, 4D10, similar configuration. But what about the last member, thallium? The last member, thallium, is abnormally different again. You see, thallium, if you take, you have a noble gas core, 4F14, 5D10, 6S2, 6P1. The point is, this is the valence shell. And see the difference in the interior configuration. 24 electrons are filled in d and f orbitals. 24 electrons are filled in d and f orbitals, which impart poor screening effect. So what is going to happen? The control of nucleus to the valence shell will increase drastically because of the poor shielding effect of f and d orbital electrons. What is shielding effect? Shielding effect means there is a lack of control or decrease in control, nuclear attraction for the valence shell due to intervening orbitals. When the intervening orbitals increases, when the intervening shells increases, control of nucleus to the valence shell decreases. This effect is called a shielding effect. Shielding effect is prominently given by s and p orbital, poor given by d and f orbital. So here, d and f orbital, which has got a poor shielding effect, will cause the nuclear charge to increase, not to decrease. So what happens? The size will decrease than what we expect. Whatever the size we are expecting, the size will be lower than what we expect. And consequently, every property related to size will be affected. Now see what happens. This is happy to involve this electron, it gives +3 state. This is happy to involve these electrons, happy to give +3 state. But as you come down here, due to increased nuclear attraction, this electron has a reluctance to take part in chemical bonding. The valence shell NS2 electron has a reluctance to take part in chemical bonding. Only this electron is willing to take part in chemical bonding. Therefore, TlCl3 is not stable, rather TlCl is stable. It is only interacting with the 6p1 electron, 6s2 electron show a reluctance to take part in chemical bonding. We call it as inert pair effect. A very important topic from the initial segment of this chapter. So these things you can find in the introductory area, inert pair effect including. This is the tabulated arrangement of various oxidation states. You can see from 13 towards 18. It's giving +3, +4, +5, +6, +7, +8. That is the maximum oxidation state. While the other oxidation state, +3, +1, +4, +2, -4, +5, +3, -3. +6, +4, +2, -2. So there can be a variability in the oxidation state, but the individual oxidation state you can find differ by a unit of 2. You see here 7, 5, 3. There is a 2 unit difference. 7, 5, 3, 1. 6, 4, 2. There is a 2 units difference. The oxidation state differ by 2 units. And a few elements of noble gases, like all of you know, xenon can give a few compounds. That's why the oxidation state is commented here. All points concerned are discussed already. A talk on first member abnormality. You see, for representative elements, this is an important point. First members are abnormal. If you talk about even S block elements, lithium is abnormal, alkaline earth metal, beryllium is abnormal. And coming to P block elements, boron, carbon, nitrogen, oxygen, all these are the first members which are available in the second period, that is the starting leading member of each family, they are showing some abnormal character, mainly due to small size and all other related to this. So due to small size, due to high electronegativity, due to high ionization enthalpy, and moreover, a very important point is they don't have d orbitals present. They are in the second period. Second period elements, all of you know, they have two shells. So the valence shell is second shell n equal to 2. N equal to 2 does not contain a d orbital. They have only 2s, 2p. They have only 2s, 2p. What is the point of characteristics with the 2s, 2p only present? 2s, 2p, I am talking about these members. Boron, carbon, nitrogen, first members in every family. They have 2s, 2p. 2s, 1 orbital, 2p, 3 orbital, a maximum of 4 orbital it can utilize for bonding. The maximum covalency limited to 4. So those typical points you can find as an introductory area over here. And yet another point is their ability to make stable pi bonds. Stable pi bonds, especially carbon, nitrogen, oxygen. They are able to make stable multiple pi bonds between each other and with the neighboring members. Between each other and with the neighboring members. For example, carbon, nitrogen, oxygen able to make CC single bond, CC double bond, CC triple bond, CN triple bond, CO triple bond, N triple bond, N double bond. So variety of pi bonds, stable p pi bonds they are able to make. Have an idea regarding what is meant by p pi bond, p d pi bond, d pi bond. What is p pi bond? What is meant by p pi? The two p orbital makes a lateral overlapping is called p pi bond. One p orbital of one atom with another p orbital of another atom making a lateral overlapping is called p pi bond. What about p d pi bond? P d pi bond. One p orbital of one atom with one d orbital of next atom making a lateral overlapping. P d pi bond. What about p d pi bond? D pi bond. That is two d orbitals. Two d orbital of one atom making a lateral overlapping with the d orbital of another atom like this. That is d pi bond. Reference coming in the textbook. Please understand, carbon, nitrogen, oxygen in particular, we can see they make themselves and with the neighboring members giving stable multiple p pi bonds, while heavy members are not so. So the such points also commented in the textbook which you can find out. If you are comparing nitrate with the phosphate, say for example, if you take nitrate NO3 minus, this is nitrate NO3 minus. This is nitrate NO3 minus. You see, nitrogen makes sp2 hybridization. sp2 hybridization. So there are 3 sigma bonds. There are 3 sigma bond, 1, 2, 3, and there is a pi bond. And that pi bond is formed by the vacant p orbital of oxygen and vacant p orbital of nitrogen, and we call it as p pi bond. See, sp2 hybridization means one p orbital is free for nitrogen. So the vacant, the free p orbital of nitrogen makes a lateral overlapping with a p orbital of oxygen to make a pi bond over this double bond area. So this pi bond is formed by, one is sigma bond, one is pi bond. The pi bond is formed by lateral overlapping of the two p orbitals, one each of nitrogen and oxygen. What about if you take phosphate? What about if you take phosphate PO4 2 minus, phosphorus 1, 2, 3, 4. There is a PO double bond, oxygen, 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 minus, minus, minus. This is PO4 3 minus. And here phosphorus makes sp3 hybridization. sp3 hybridization means the p orbitals are completely used to make 4 sigma bonds. Sigma bond 1, 2, 3, 4. And this is a pi bond. And this pi bond is formed by p orbital of oxygen. What about phosphorus? In phosphorus, the p orbital is already used for sigma bond. Then how makes a pi bond? It is using d orbital of p phosphorus. Phosphorus is in the third period. It has got a third valence shell and it has got vacant d orbital. And it is due to that vacant d orbital, there is a pi bond formed, p pi d pi bonding here. P pi d pi bonding observed here. Hope you understand. So in nitrate, if you have p pi bonding, in phosphate we have p pi d pi bonding. So such characterization and examples are quoted in the textbook. Now on to boron family in DTL. Boron family in DTL, as I was talking, in many situations, if we talk about a particular family, atomic and physical properties dealt in the tabulated form, we need to have a meticulous analysis. Let's have a look at the atomic and physical properties of boron family members. Let's try to go through. Atomic number, atomic mass, electronic configuration, very, very important. You see boron, 2s2 2p1, aluminium 3s2 3p1, similar configuration. There will be a gradation in the property. As one shell is added, size will increase. There will be a gradation in property. What about gallium? What about gallium? We have argon 4s2 4p1, but you see there is 3d10. That 3d10 makes a good influence over the properties because d orbital got a poor shielding effect. It will affect the nuclear attraction. It will cause a greater nuclear attraction due to poor shielding effect. So the size will decrease than what we expect. You look at the atomic size, 88, 143. It's a good increase. That is what we are expecting. What about here? The size is decreasing. So actually 88, 143, well and good. It should be some 160, 170. It's 135. Have a look at that. It is due to that electronic configuration speciality what you find in gallium. Now gallium, indium quite similar. And that is reflecting in the size 135, 167. Good. It's an increase, good increase. But what about thallium? Thallium when you come, there is a noble gas core 6s2, 6p1. What about this? F4F14, 5d10. There are 24 electrons filled in D and F orbital. So what? D and F orbital has got poor shielding effect, poor screening effect. So what? It is unable to give shielding power. It is unable to give shielding. So what? The nuclear attraction will increase beyond a natural thing. What we expect is a decrease. Here the nuclear attraction increases due to poor shielding effect. So the atomic size will be affected. You see this 167. This must be in and around 200, right? 167. This should be in and around 200. But look at the data 170. So the expected data should be somewhat in range of 200. You see 88, 143. It should be 167. It should be somewhat 200. The value is 170. So there is a decrease in size than what we expect, which is happening due to increased nuclear attraction, which is caused by poor shielding effect of D and F orbital electron. What happens is, due to increased nuclear attraction, this electron will act as an inert pair. The 6s2 electron act as an inert pair, and they are not contributing much on to the bonding characteristics. Therefore, only these p1 electrons are contributing for bonding. Try to understand. And not only that, it is affecting the size. When it is affecting the size, every property related to size will be influenced. like ionization enthalpy, electronegativity, every property which are closely related to atomic size will be affected. Hope you get the picture. So there is a clear observation you need to meticulously have a look at. Boron, aluminium. After aluminium, there is a change. Gallium, indium, regular trend. After indium, thallium, there is a significant change that you can experience throughout in the table. You see ionization enthalpy, 3 ionization enthalpies are given because there are 3 valence electrons. You see 801, 577, there is a decrease, but here there is an increase. It should decrease actually. Now from here to here it decreases, but here there is an increase. It should decrease actually. It is increasing. Look at electronegativity 2, 1.5. It is decreasing, but here it is increasing. So ionization enthalpy, electronegativity, all related parameters will be influenced by that particular difference in the electronic configuration. 1.6, 1.7, 1.8, it is increasing. Similarly, try to have a look at the entire data like that, melting point, boiling point, etc. And there is standard potential also given. Standard potential given for M3 plus bar M plus bar M. Oh, hope all of you know what is the result of analyzing standard reduction potential. If you have a negative data, high negative data showing a good reducing agent. If you have a high negative data like this, it indicates this is a very good reducing agent. Similarly, if you have a positive data, that indicates this is a good oxidizing agent. All of you know how to analyze. I will make a generalization, even if you are aware of, you see, E naught value A bar B. Suppose it is a high positive figure. What does that mean? That means this is easily reduced to this. This is a good oxidizing agent and this is stable. Suppose you have E naught value X bar Y given high negative value. What does that mean? This is easily oxidized to this. This is a very good reducing agent. This is stable. Like that. So try to investigate about the standard reduction potential data given in that context. Not available in all the species, but a few are given, especially boron is not given because ionized form of boron is not available because of the large sum of 1, 2, 3 ionization enthalpy values. The sum of IE1, IE2, IE3 is a large value. Therefore, you don't get boron as an ionic form like you get aluminium. Boron does not give B3 plus ionic form. Okay. So this is the analysis, a meticulous analysis on the data concerned to atomic and physical properties of group 13, that is boron family, which in detail is also explained somewhere over here. You can find the electronic configuration, atomic radii, ionization enthalpy, etc. Electronegativity, physical properties are dealt here, which is commenting boron, non-metallic in nature. All of you know boron is non-metallic in nature. And of course, it has got applied as a doping material, some sort of semi-metallic character. Aluminium onwards, all are metals. Extremely hard and black colored solid, several allotropic forms. It has got an unusually high melting point. And an unusual low melting point is given by gallium. Gallium has got a very low melting point. It melts when you take in your hands. The body temperature is enough to melt a gallium, but the boiling point is very high. Boiling point is very high. Like that, the physical properties are commented, and our discussion on chemical properties on group 13. Chemical properties on group 13, right? And chemical properties, oxidation state and trend in chemical reactivity. Oxidation state and trend in chemical reactivity. See, as far as boron is concerned, small size boron, the sum of its first three ionization enthalpy is very high due to, already commented, due to small size, boron has got a high ionization enthalpy. That too, the sum of ionization enthalpy 1, 2, 3, there are 3 valence electron, it is very high. Therefore, you are unable to get boron in the +3 ionic form. Boron is not available as boron 3+ ionic form, while aluminium is available. So aluminium you can get it in the ionic form. Boron you cannot. Right? So the oxidation state will be group oxidation state. It is group number 13 minus 10 plus 3. That is the group oxidation state. Group oxidation state is well behaved by boron, aluminium like top members. As you come down, already discussed in the topic, inert pair effect. Due to inert pair effect, the +3 stability decreases and +1 stability increases. The +1 stability, +1 oxidation state increases in the order aluminium minimum, gallium next, indium next, thallium maximum. So down the group, +1 group, +1 oxidation state stability increases and +3 stability decreases. Inert pair effect, already commented. So that is main point dealt in chemical properties, which already we have seen. Now, what next? Some important point we can see is regarding the Lewis acid character of group 13 elements. Group 13 compounds are generally electron deficit in nature. They have sextet electron system and they don't have octet system. It is incomplete octet. Incomplete octet. Look at the planar BCl3. Look at planar BCl3. It's around the central boron. We have how many electrons? You can take an account. It will be 2 electron here, 2 electron here, 2 electron here. It is a sextet system. And it is electron deficient and it can act as a Lewis acid. It can react with a molecule like ammonia and forms a addition product, and thereby you get a tetrahedral addition product. And here this is acting as a Lewis acid and this act as a Lewis base. What is meant by Lewis acid, Lewis base? Electron pair acceptors are called Lewis acids. Electron pair donors are called Lewis bases. Ammonia donate a pair of electron, Lewis base. BCl3 or BF3 accept a pair of electron called Lewis acid. Okay. Similarly, AlCl3, a compound from the same group, it is electron deficient. That will make the electron deficiency compensated by forming a dimer. AlCl3 exists as a dimeric form, Al2Cl6. This is Al2Cl6, which is tetrahedral center across the aluminium atom. It is tetrahedral system. There is chloro-bridged dimer. The exterior bond angle 118 degree, while interior bond angle 79 degree. When the bond angle decreases, you can see bond length will increase. Bond length is 221 here, while the exterior bond length is 206. Bond angle and bond length are related. So exterior bond angle greater, bond length lower. Interior bond angle lower, bond length greater. Right? So all these can come as a question. So molecular dimensions, if any, given in the textbook, you are supposed to go through that. You see that aluminium forming octahedral hydrated form, where it is sp3d2 hybridized. Octahedral sp3d2 hybridized. AlH2O 6 times. While usually it will make tetrahedral MOH 4 times. So I don't have to tell you boron. will form only tetrahedral system, while aluminum can extend up to octahedral system. Boron is the second period member. Its covalency maximum limited to 4, already discussed. There are problems connected to standard reduction potential and its application. How to apply standard potential, already commented. Next is reactivity towards air. Reactivity towards air. How boron family elements react with the air. Let's have a look at. Boron is unreactive in the crystalline form, and aluminium forms a very thin oxide layer on the surface which protect the metal from further oxidation. So aluminium forms a thin oxide layer over the surface and that prevent further oxidation, while elemental boron is unreactive in the crystalline form, while amorphous boron and amorphous aluminium can, upon heating, you can get B2O3 and Al2O3 respectively. What is the nature of B2O3 and Al2O3? Acidic, amphoteric, basic, neutral. What is the nature of B2O3? B2O3 is acidic in nature, while Al2O3 is amphoteric in nature. B2O3 is acidic in nature as it is giving boric acid. This, upon hydrolysis, you get H3BO3, boric acid, while this is amphoteric in nature. Aluminium oxide is amphoteric in nature, boron oxide is acidic in nature. Boron oxide will give you boric acid. Okay. See, E means the element. E means the element that will give you E2O3 and En. For example, AlN, aluminium nitride, Al2O3, aluminium oxide. The nature of these oxides is already I have commented. I have already commented. This is acidic oxide. This is acidic in nature, while this is amphoteric in nature. Already commented. Next is reactivity towards acids and alkalis. Reactivity towards acids and alkalis. How they react with the acids and alkalis. Boron does not react with the acids and alkalis even at moderate temperature, but aluminium dissolve in mineral acids and aqueous alkalis, showing amphoteric behavior. Aluminium can react with HCl and aluminium can dissolve in NaOH. Aluminium dissolved in HCl, you get AlCl3 and hydrogen gas is liberated. The same aluminium dissolved in NaOH, giving sodium tetrahydroxoaluminate. Sodium tetrahydroxoaluminate, liberating hydrogen. So, hydrogen gas is liberated by aluminium, both in acid medium as well as in alkali medium. But there is an important point to be seen. What is the important point to be seen? However, concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. So aluminium reacts with the dilute HCl liberating hydrogen gas. But aluminium made passive, aluminium rendered passive by reacting with the concentrated nitric acid. What is happening? When it is treated with the concentrated nitric acid, is an excellent oxidizing agent. It will oxidize the top layer surface of metallic aluminium to aluminium oxide. So aluminium turned aluminium oxide. And the aluminium rendered passive. Aluminium oxide is highly stable that prevent further reaction. A thin film of oxide layer formed over the surface of aluminium prevent any subsequent reaction. Okay, that is an important point from that segment. Next is reactivity towards halogens. Reactivity towards halogens. All the elements react with the halogen to form trihalides except TLI3. You don't get TLI3. Number one, thallium is not interested to give +3 state. Number one. Number two, three large iodine atoms does not thermodynamically and even kinetically does not favor the formation of TlI3. So TlI3 does not exist. Multiple reasons. Thallium unfavorable to give +3 state. Inert pair effect. Number one. Iodine is larger atom, so it is not comfortable to make TlI3. Another reason. Many reasons can be incorporated. TlI3 does not exist, while others are giving trihalides. The important trihalides of boron: Bf3, BCl3, BBr3, and Bi3. They all act as Lewis acids, and the minimum Lewis acid character increases down the group. Minimum Lewis acid character is Bf3 due to a special scenario called back bonding. Due to back bonding, Bf3 is minimum Lewis acid character. See why or how they act as Lewis acids. How they act as Lewis acids? Because of electron deficiency. Because of electron deficiency, they act as Lewis acids. Bf3. It is electron deficient, having only 6-state system. Only 6 electron system. But that electron deficiency may be somewhat compensated by a phenomenon called back bonding. What is back bonding? Here boron undergo sp2 hybridization. Therefore, one p orbital is vacant. One p orbital is vacant. Similarly, we have p orbital with the fluorine, which is not vacant, which contain electrons. You know, fluorine contain 3 lone pair of electrons, and that is available in the p orbital, and this fully filled p orbital is migrating to vacant p orbital, and there is a back donation. It is called a back donation or back bonding. Back donation or back bonding. And due to back bonding, not only from one fluorine, from this fluorine and this fluorine, due to back bonding, you can find there is a partial double bond character between boron and fluorine, and the electron deficiency of boron is somewhat compensated by this back bonding, and thereby the situation is it is having a partial double bond character between boron and fluorine, and electron deficiency of boron is somewhat compensated, and this back bonding is maximum happening with the Bf3. What about BCl3? Suppose we come to BCl3. What is happening? We have the same scenario. We have boron and 3 chlorine atom. It is electron deficient, but the back bonding effect is less compared to this. See what is happening here. Again boron, it is sp2 hybridized, and one p orbital is free and vacant. And we know chlorine also contain lone pair of electron the way fluorine has. But you see the difference. You see the difference. Here we have chlorine with the full of electron, but the effect of back bonding will be less, because what is the reason? It is there in the board. See, this is 2p orbital, and this is also 2p orbital. This is 2p orbital, but this is 3p orbital. It is larger in size and larger in higher in energy. So there is a difference in size and energy of 2 orbitals. Here both are same energy, same size orbital, so there is an effective overlapping. Here the orbitals are different size and different energy, so back bonding will be there, but the effect of back bonding will be less compared to this. So here the electron deficiency is compensated by back bonding. Here the electron deficiency is compensated by back bonding, but to lesser extent compared to this. That is what happened. I was talking about the Lewis acid nature of boron trihalides. The order will be Bf3 minimum, BCl3, BBr3, like that. That is not in the NCERT, but that's an important point. Next is anomalous properties of boron. Anomalous properties of boron. Nothing specific to comment. Boron is first member and it is anomalous in nature. What are the anomaly? Reason for anomaly of boron. Number one, small size. Number two, high ionization enthalpy. Small size, high ionization enthalpy. The sum of 1, 2, 3 ionization enthalpy is very high. Therefore, it does not form ions. Most importantly, its coordination number limited to 4. It has a maximum covalency limited to 4 as it belongs to second period. The second period elements will have two two shells, and second shell is the valence shell which contain 2s and 2p orbital. 2s 1 orbital, 2p 3 orbital, and total 4 orbital. Therefore, maximum covalency limited to 4. While aluminium and heavy members, they can go coordination up to 6 or even more. That is the most important aspect of dealing with the anomalous property. There are questions like this: boron unable to form BF6. Yes, boron cannot give BF6 because the maximum covalency limit for boron is 4. So like that, simple questions available. Now we need to continue the discussion. Some important compounds of boron. Some important compounds of boron. Number one, a talk on borax. Number one, a talk on borax. One of the most important compound of boron, borax. Borax having the formula, it's a white crystalline solid having the formula Na2B4O7 10H2O. Na2B4O7 10H2O, and the original formula will be like this: B4O5OH 4 times. It is Na2B4O5OH 4 times 8H2O. Look at the borax formula and the details. Borax is Na2B4O7 10H2O. Borax, the crude borax in India, we call it as tinkal powder. Tinkal powder. The original formula we can write Na2B4O5OH 4 times 8H2O. It's like this: Na plus O minus B O B O B O B, like this. 1, 2, 3, 4 boron and 2 O minus. You have 2 Na plus and 8 water molecule, and each boron will contain OH group. This is the linear format of borax. This is the linear molecular format of borax. You see that? Boron 1, 2, 3, 4 boron. Oxygen will be 5. How 5? 1, 2, 3, 4, 5. As many boron, as many OH. OH, 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 OH. 4 boron, 4 OH. So 4 boron, 5 oxygen, 4 OH. That is a linear format. Actually, borax is not existing in the linear form. It is, see, such a long chain cannot exist stable. Rather, it will form a cyclic ring type structure. So, borax originally is having this characteristics. Borax originally can be represented like this: boron, oxygen, boron, oxygen, boron, oxygen, boron, like this. Now connect this boron with the oxygen, and there will be OH here, OH here, OH here, and OH here. And this boron will be minus, and this boron will be minus. Quite naturally, there is Na plus, and there will be 8 water molecules of hydration. This is the structural entity of actual borax structural entity, where there are 2 types of boron you can find in the structural identity. One type is this one, which is sp3 and tetrahedral, same as this one. This is sp3 tetrahedral. So out of 4 boron, 2 boron is sp3 tetrahedral. What about the other 2 boron? Is it same? Look at this boron and this boron. It is different. It is what hybridization? This is sp3 and tetrahedral. You can find it like this. Okay. What about the other 2 boron? It is sp2 and planar. It is sp2 and planar system. Is it clear? So out of 4 boron, 2 will be sp3 tetrahedral and the other 2 will be sp2 planar. That is an important point to understand. This is sp2, this is sp2, this is sp3 and this is also sp3. Is that clear? I believe. Right? That is about the structural identity of borax, which is normally represented Na2B4O7 10H2O. Right? And borax dissolve in water giving alkaline solution. Borax dissolve in water giving alkaline solution. See, borax is a salt of weak orthoboric acid and strong NaOH. Borax is a salt of weak acid and strong base. Quite naturally, it is alkaline solution. It's a salt of weak boric acid and strong NaOH. So the solution, quite naturally, it is alkaline in nature. Number 1. Number 2, on heating borax, it first loses water of crystallization. On heating borax, it first loses water of crystallization. And you get anhydrous borax. You get anhydrous borax. This is gone. And you get anhydrous borax, which upon further heating, you get sodium metaborate and boric anhydride, which swell up to form a glassy, transparent glassy mass, which we call it as a glassy bead, borax bead. You take a platinum wire loop and keep some borax there and heat it strongly. Initially, water molecules will be out and you get anhydrous borax. After some time, it turns a transparent glassy bead. And that is borax bead used for testing transition metal and their compounds. And borax bead is formed by nothing but chemically, it is sodium metaborate and boric anhydride. This can be used for testing transition metal and their compounds. How? The metaborates of many transition metals have characteristic color and therefore borax bead test can be used to identify them in the laboratory. For example, when borax is heated in a Bunsen burner with cobalt oxide, you will get blue colored cobalt metaborate is formed. So transition metal metaborates are colored in nature. They have colored characteristic color as we find in the textbook. Cobalt will form cobalt metaborate, which is blue in color, or blue color can be taken as a test for cobalt compounds. Similarly, different transition elements and their compounds will give characteristic bead test. How do we do that? Take a platinum wire loop, keep borax there and heat it strongly until you get a transparent glassy bead. Now, the given transition metal compound is kept over that and heat it again. Now, the transparent glassy bead turn a beautiful colored bead. The color of the bead will tell you what transition metal compound you are dealing with. For example, cobalt will give you blue coloration like that. So what all facts regarding borax? Borax formula, borax structural entity, the cyclic ring type structure of borax, an aqueous solution of borax turning alkaline, borax bead test. These are the important area from borax. Next is boric acid. The so-called orthoboric acid. Orthoboric acid, it is H3BO3, a white crystalline solid with a soapy touch. A white crystalline solid with a soapy touch. sparingly soluble in water but highly soluble in hot water, and can be prepared from any boron compound. Any boron compound undergoing hydrolysis, you get boric acid. Say for example, borax undergoing hydrolysis, you get boric acid. Boric acid can be written as H3BO3 or BOH 3 times. BOH 3 times. This is orthoboric acid. Once again, boron is sp2 hybridized and the structure entity is planar entity. Right? It can also be found by hydrolysis of most boron compounds, maybe halide, hydride, etc. You will get boric acid. Boric acid is a weak acid. Boric acid is a weak acid. It is a aprotic acid. It is a Lewis acid. It is a monobasic acid. How does boric acid work? How does boric acid work? Boric acid is a aprotic acid. See how boric acid is working. BOH 3 times. BOH 3 times. Interact with the water molecule and it exists under equilibrium. It is breaking over here and OH minus is withdrawn by boron, and thereby you are getting BOH 4 times. BOH 4 times minus plus H plus. So this H plus is actually derived from water. H plus is actually derived from water. So H3BO3, boric acid, absorb OH minus. This is a Lewis acid. Right? This is a Lewis acid and want a pair of electron. That pair of electron is made available from OH minus. It is interacting with OH minus. OH minus is withdrawn and thereby we are getting H plus. So H plus is not provided from its own. It is a aprotic acid. It is not a protic acid. It is a Lewis acid. It is a weak acid. And the titration procedure is very tough to identify the endpoint as it is a weak acid. To make it act as a strong acid, we add some polyhydroxy compound, sugar, glucose, some glycols, ethylene glycol, etc. Polyhydroxy vicinal diol molecules can be used for increasing the acidic nature of boric acid. And if you add some ethylene glycol, if you add some glycerin, if you add some sugar, glucose, etc., some vicinal diols, that is enough. You can see the equilibrium is shifting far towards right hand side and the weak boric acid acts as a reasonably good strong acid. How? Try to identify of your own. Not in the text. I'm just asking you, I'm leaving to you to identify that particular point. So usually when we do the titration procedure with the boric acid, we used to add say a small amount of sugar. Thereby the equilibrium is far shifting to right hand side and we are able to identify the titer point comfortably. What is the logic behind? You just try to identify. So that is about boric acid. This is what I have written now. BOH 3 times with water, you are getting BOH 4 times minus and hydronium ion. Now, boric acid on heating. Boric acid on heating. First you will get metaboric acid and then you will get tetraboric acid. Upon red hot heating, you will get boric anhydride. So boric acid upon heating, first you get metaboric acid, HbO2. Then further you get tetraboric acid, not written here. Further heating to red hot condition, you get boric anhydride. Right? Keep it in mind. And this is the structural entity of solid boric acid. It is forming a hexagonal sheet-like structure. Hexagonal sheet-like structure. How many molecules undergoing hydrogen bonded? It is due to hydrogen bonded condition. How many molecules are undergoing hydrogen bonded? This is one boric acid molecule. That is one boric acid molecule. That is hydrogen bonded. One here, one here, one here, one here, one here. So you can find How many hydrogen bonded condition? Let me illustrate, let me explain once again. You see, this is boric acid. Where is boric acid? This is one boric acid. This is one boric acid molecule, right? It is hydrogen bonded around other molecules. Oh, it's gone. It's gone. Let me show that once again. The hydrogen, the boric acid molecule, one, this is boric acid molecule. It is hydrogen bonded to how many nearby molecules? How many nearby molecules? It is one here, it is one here, it is one here, one here, one here, one here. Isn't it? One over here with the hydrogen, one over here with oxygen, one over here with the hydrogen, one over here with the hydrogen, one over here with the hydrogen. You see that? So 1, 2, 3, 4, 5, 6 places. One boric acid molecule makes hydrogen bonding with the 6 places surrounding, forming a hexagonal sheet-like structure. I am sure many of you know boric acid as a household material. What is boric acid? How many of you seen boric acid? How many of you used boric acid? It is known to all. It is known to all. It is nothing but boric powder, carom powder. This is used as carom powder for reducing the friction of moving coins. You see, it makes a sheet-like structure, so it has got a slippery action. That sheet-like structure make a slippery action and can act as a solid lubricant, which help to reduce the friction between the moving coin and the surface of the coin, the carom board. It's used as carom powder, known to all. That is about boric acid. That's all about boric acid. Now, what next? Next is a talk on diborane. Next is a talk on diborane. Let's have a look at diborane. Formula B2H6 diborane, the simplest boron hydride known. There are a variety of classes of boron hydrides. Nidoboranes, arachnoborane, so many variety of boranes like hydrocarbons, not to that extent. Simply, there are some varieties available. The simplest boron hydride is diborane, prepared by heating BF3 with lithium aluminum hydride. You can get a diborane. BF3 with lithium aluminum hydride. You can get a diborane. While a convenient laboratory method involves oxidation of sodium borohydride with iodine. Oxidation of sodium borohydride with iodine. That's a convenient method in the laboratory preparation. Oxidation of sodium borohydride with iodine. You get a B2H6. Or industrial scale, it can be prepared by the action of BF3 with NaH. BF3 with the sodium hydride. We get a B2H6 industrially prepared, which is a colorless, highly toxic gas, boiling point 180 Kelvin, catches fire spontaneously upon exposure to air. So toxic gas, colorless gas, immediately catches fire, and the reaction is highly exothermic. 1976 kilojoule energy is liberated. And even the higher boranes are spontaneously flammable in air. Boranes are readily hydrolyzed by water to give boric acid. Already commented. Boron compounds, whether chlorides, hydrates, etc., readily hydrolyzed to get boric acid. Already commented. Boranes are readily hydrolyzed, already commented. Diborane undergoes cleavage reaction with the Lewis bases to give borane adduct. Diborane react with what is NMe3, trimethylamine, NCH3 thrice, NCH3 thrice, trimethylamine. So diborane react with trimethylamine. All of you know there is a lone pair of electron that will be donated to make a bond. That will be donated to make a bond. So the lone pair of electron with the nitrogen is donated to make a addition reaction with the diborane. The lone pair of electron with the carbon monoxide used to add with the diborane. So you get addition product with the Lewis bases like NME3 or trimethylamine. Carbon monoxide contain a lone pair of electron, can act as a good ligand like that. This is one of the important paragraph, I would say. Diborane react with ammonia. Diborane react with ammonia. First you get B2H2. First we are getting B2H6 2NH3. And that is originally formulated like this. B2H6 2 ammonia can be understood as BH2 NH3 twice whole plus BH4 minus. That's a previous question. Ammonia interact with the diborane gives initially. This is the answer. On further heating, you get B3N3H6. All of you may be remembering inorganic benzene. Inorganic benzene. What is inorganic benzene? It is isostructural with benzene. Inorganic benzene is isostructural with benzene. B3N3H6. BN like this alternately. B3N3H6. Isostructural with benzene. Isostructural with benzene. This is inorganic benzene, B3N3H6. Right? Inorganic benzene, an important compound obtained when heating diborane with ammonia. It gives variety of products. Boron nitrides. Boron nitrides are important variety of products. BNX. BNX. Boron nitride. And is available as hexagonal sheet-like structure like graphite, and extremely strong variety like a diamond, cubic structure diamond available. So you get various class of product reacting diborane with the ammonia, right? And finally, the structural details of diborane. Structural details of diborane. This is the structural details of diborane. You see, two boron are available in a plane. Two boron are available in a plane. Two boron are available in a plane and 4 hydrogen atom available in the same plane. So 2 boron and 4 hydrogen atom available in a plane, while 1 hydrogen atom is hanging above the plane of the paper. It is a bridged bond. And 1 hydrogen atom below the plane of the paper. So 2 hydrogen atom, one above and below like this. 2 hydrogen atom, one above and below like this. They are called a 3-center 2-electron bond. That is referred as 3-center 2-electron bond. See, it is coming like this. We have a plane where we have 2 boron like this and 4 hydrogen atom in the corners of the plane like this. And now 1 hydrogen over here and 1 hydrogen over here. And that is actually perpendicular to the plane. It's available like this. It is a 3-center 2-electron bond. Here we make use of usual 2 electron. Here we make use of 2 electron. Here we make use of 2 electron. Here there is 2 electron. Here there is 2 electron. While here it is 3 atomic centers governed by a total of 2 electrons. This center, this center, this center. It is governed by 2 electrons as a whole and is called a 3-center 2-electron bond. 3-center 2-electron bond. Similarly, here also. So top and bottom, above and below the plane, there is 3 center 2 electron bond like this. While in the plane, there is 2 center 2 electron usual covalent bond, 4 bonds. That is the structural feature of diborane. It makes sp3 hybridization. It is making sp3 hybridization. And the geometry could be understood like this. One boron, this is one sp hybrid orbital, this is another sp hybrid orbital, this is another sp hybrid orbital, and this is fourth sp hybrid orbital. These orbitals are electron filled orbital, while one orbital is vacant orbital. And the next boron, similarly, it is having a vacant hybrid orbital and 3 fully filled hybrid orbital. This is fully filled orbital, while this is a vacant orbital. So vacant orbital of this boron and fully filled orbital of this boron overlaps. Similarly here, vacant orbital of this boron and fully filled orbital of this boron will overlap. And you can find the hydrogen comes and binding in the respective manner. Here one hydrogen comes and bind. Here one hydrogen comes and bind. Here one hydrogen comes and bind. And here one hydrogen comes and bind. That is usual 2 center 2 electron bond. While this overlaps to make a electron density where one hydrogen comes and bind here. And this overlap like this and one hydrogen comes and bind here. And we call it as, all of you might have heard about and remembering, banana bond. Banana bond. That's a 2 electron, 3 center, 2 electron bond. Why it is called a 3 center, 2 electron bond? Why it is called a 3 center, 2 electron bond? Nuclear center 1, nuclear center 2, nuclear center 3. 3 center, 2 electron bond. Right? So there are 3 center, 2 electron bond, 2 numbers. And 2 center 2 electron bond, 4 numbers. That is about the structural feature of diborane, and it's actually a adjustment bond. These two bridging bonds are adjustment bond because of electron deficiency. And the molecule is highly unstable and it may rupture at any moment because it is an unstable bond holding that bridging hydrogen. This is what the nature of diborane molecule, structural feature of diborane molecule. Next, uses of boron aluminum. Let's see some important points available there. Uses of boron aluminum. Boron being extremely hard, refractory solid, high melting point, low density, very low electrical conductivity. Boron fibers used in bulletproof vest, high composite material, aircraft. Boron 10 isotope has high ability to absorb neutrons. Therefore, metal borides used in nuclear industry as protective shield and control rods. Borax and boric acid, manufacture of heat resistant Pyrex glass. Borax used as a flux for soldering purpose. Heat scratches, stain resistant glazed coating, earthenwares, constituent of medicinal soaps. An aqueous solution of boric acid generally used as mild antiseptic. Boric acid used as mild antiseptic. Aluminium, bright silvery white metal, high tensile strength, high electrical thermal conductivity. You can see a comment on weight to weight basis. Electrical conductivity of aluminium twice that of copper on a weight to weight basis. Electrical conductivity of aluminum, double that of copper. Extensively used in the daily life, various alloys, packing, utensil making, construction, aeroplane. Aluminum is very popular, known as flying metal. Various alnico alloys and related materials used for the construction of aircraft components. Yes, that's all about group 13. There we conclude group 13, boron family. We had an exclusive discussion about borax, boric acid, diborane, inorganic benzene, etc. and normal properties. Now on to group 14, carbon family compounds. Group 14, carbon family compounds. All of us know group 14 carbon family, carbon, silicon, germanium, tin, lead and flerovium. The new member 114, flerovium. Carbon, 17th most abundant element. Available as coal, graphite, diamond, mostly in the combined form. Carbon dioxide in environment 0.03% by volume. Organic chemistry highly devoted to carbon and its compounds. We call it as hydrocarbons and derivatives. Organic chemistry, organic compounds. Two stable isotopes, carbon 12, carbon 13. Two stable isotopes. And there is a third isotope, carbon 14, which is radioactive in nature and used for radiocarbon dating. The half-life being 5770 years. Molecular clock, radiocarbon dating. If we get some fossils and all, using radiocarbon dating, we can approximate the life of that species which was lived in the earth. For example, if we get a fossil sample, we get a small portion and burn it and see the carbon 14 content in it, what is the rate of decay? Suppose we find that it is some 25% decay giving. So we can understand 75% decay over. That means 75% means T75 will be 2 T half. 2 T half means approximately 2 times 5770 years it was lived in the earth. Like that, molecular clock, what do you call, method adopted or explained or introduced by scientist named Libby. Silicon, second most abundant element. So goes like that. So general introduction regarding the elements of group 14. Silicon dioxide, SnO2 called cassiterite, lead sulfide called galena, a small talk on flerovium, nothing more because its chemistry is not explained because it's highly radioactive in nature. Now on to atomic and physical properties of carbon family as we were doing in the boron family. Carbon family elements, atomic and physical properties of carbon family elements. Let's have a look at in detail. Atomic number, mass number. Let's have a look at electronic configuration. Very important. Here you can see carbon and aluminium. Carbon and silicon maintaining identical configuration with the one shell extra. 2s2 2p2, 3s2 3p2. So carbon family elements end up with the configuration ns2 np2, ns2 np2, and that is how their covalency coming 4. How is that covalency coming 4? ns2 np2, that is the system. ns2 np2, say for example carbon, the valence shell is atomic number 6, 1s2 2s2 2p2. This is inner shell and this is valence shell. 2s orbital, there are 2 electrons and 2p orbital, there are 2 electrons. In the excited condition, one electron will be switching to this orbital, and we have 2s orbital, 1 electron, and 2p orbital, 1 electron each, and we have 4 covalency. 4 covalency, right? For example, methane, we get 4 covalency according to this condition, and mostly their group oxidation state and the maximum oxidation state found to be 4. And that is evident from the electronic configuration. That is clearly evident from the electronic configuration. So the configuration of carbon and silicon quite similar. What about germanium? If we come to germanium, we can see the electronic configuration, of course, noble gas core and 4s2, 4p2, but you can find there is 3d10. There is 3d10 configuration, and that makes the d orbital having poor shielding effect. That makes a abnormal character in the size due to increased nuclear charge. So the poor d orbital shielding effect, the nuclear charge increases, size will decrease, and that will reflect the way we were discussing in group 13 boron family. We have gone through boron aluminum, similarly maintaining the trend. But after aluminum gallium, there is some abnormality. Similarly, carbon silicon, after that germanium, there will be some sort of abnormality. And germanium and tin, it will be quite similar. You see, noble gas, 4s2, 4p2, 5s2, 5p2, there is 3d10, 4d10. It is similar electronic configuration. It is similar electronic configuration. Quite naturally, these two will maintain the trend. These two will maintain the trend. From here to here, there will be a difference. Now, of course, the last member, there will be a difference. What is the difference? We have noble gas core and 6s2, 6p2. But here we have again abnormality where 24 electrons are filled in f and d orbitals. 4f14, 5d10. 24 electrons filled in f and d orbital, which has got a very poor screening effect, and due to which the control of nucleus to the valence shell will increase quite naturally. Due to that increased nuclear charge, we see that the control of the nucleus when increases, the valence shell 6s2 electron is unable to take part in chemical bonding. They are unable to take part in chemical bonding. They show a reluctance to take part in chemical bonding, and only these 2 electrons take part in chemical bonding. Inert pair effect. We have discussed it in the previous group also. Coming to covalent radius 77, 118, considerable increase, but 118, 122, small increase only. 122, 140, good increase, but 140, 146, only small increase. So, from here to here, there will be some abnormality. From here to here, there will be some sort of abnormality. Ionic radius, etc. Ionization enthalpy. 4 ionization enthalpies are given, indicating 4 valence electrons. Let's have a look at the trend. 1086, 786. There is a good decrease. But 786, 761, it is not so good decrease. It is decreasing, but only small decrease. 760, 708, good decrease. 708, 715, you can see the abnormality. It is not decreasing, rather it is increasing. So that is what the abnormal scenario we find. Carbon, silicon, there will be a trend. Silicon, germanium, there will be some change. Germanium, tin, there will be trend. Tin to lead, there will be an abnormality. Inert pair effect, which is contributed to the electronic configuration speciality. Electronegativity, 2.5, 1.8 decreases, but 1.8, 1.8, 1.8, 1.9, you see it is increasing. So, the size and the consequential the properties getting reflected over ionization enthalpy, electronegativity, etc. Density, you can go through if there are some abnormalities, Melting point decreases down the group. High melting is 4373, should be diamond. Then silicon, it goes like that. Abnormal low value for tin, 505 only. Boiling point goes like that. So these are the important atomic physical properties concerned to group 14, which are illustrated or explained in detail: electronic configuration, covalent radius, ionization enthalpy, electronegativity, anything else. Physical properties, anything special in the physical properties? All are solids. Carbon, silicon, non-metals. Carbon, silicon, non-metals. Rather, silicon is having some sort of semi-metallic character. Germanium is a metalloid. Tin and lead, soft metals with a low melting point. That is about the physical properties. Coming to chemical properties. Any important points which we need to review from the chemical properties than we were commenting so far? They have oxidation state +4 and +2. +4 state is dominant state, especially on top of the group, carbon, silicon, etc. As you come down, the stability of +4 state decreases and +2 state increases. Rather, for lead, the most stable oxidation state is not +4, +2, inert pair effect. The sum of first 4 ionization enthalpies of carbon very high. Therefore, it is giving only covalent compounds. It doesn't give any ionic compound. +2 tendency decreases down the group, inert pair effect. Carbon, silicon showing +4 state. All things we have commented. Tin forms compounds in both oxidation state. Tin +2 state is reducing agent. Tin +2 state is reducing agent. SnCl2 will be converted to SnCl4. That's how it acts as a very good reducing agent used in various organic reactions, including SnCl2 +2 state will be converted to SnCl4 +4 state. So it undergo oxidation and act as a good reducing agent. Lead +2 state are stable. Therefore, lead +4 will be good oxidizing agent. +4 lead, PbO2 is a good oxidizing agent. PbO2, lead in the +4 state, will be converted to PbO, lead in the +2 state. It undergo reduction and it acts as a good oxidizing agent. So tin 2+ act as a reducing agent, while lead 4+ act as a good oxidizing agent. And generally, the compounds formed by carbon family will be electron precise compounds. They form electron precise compounds. For example, CCl4 or any such molecule, they will form electron precise molecules. CH4, for example, they have octet. And there is 8 electron system, and all the electrons are utilized for bonding. They are electron precise molecules, while group 13 are electron deficit molecules, act as Lewis acids. Group 14 compounds are electron precise molecules, while group 15, 16, 17 are electron rich molecules generally. So usually this form electron precise compounds. And regarding carbon, we know the maximum covalency will be limited to 4, not only for carbon, beryllium, boron, carbon, nitrogen. We know all these members lying in the second period. That is the first member of every family. They have abnormal properties. And one of the important abnormality is nothing but they show maximum covalency 4. How that maximum covalency 4? Already explained. This is their maximum covalency. They have 2s orbital and 2p orbital. 4 orbital ready for bonding. they don't have d orbitals present. I'm talking about the first member. Carbon, boron, nitrogen, beryllium. I'm talking about the first member. Their covalency is limited to 4. So these kind of points are described over here. While the heavy members, they can go for higher coordination. Silicon can give 6 coordination, germanium can give 6 coordination, tin can give 6 coordination, and the hybridization will be sp3d2 hybridization, octahedral geometry. This is regarding the general trend of chemical properties concerned to group 14 carbon family. Let's have a talk on individual reactions. Number 1, reactivity with oxygen. Reactivity with oxygen. They form 2 types of oxides, monoxide and dioxide, MO and MO2. 2 types of oxides are formed, MO and MO2. And there are some important points in this paragraph. What are the main points which you can see? MO, MO2. SiO only exists at high temperature. That is point number 1. Most important point is the acidic amphoteric behavior of these oxides. Very, very important. You see that carbon dioxide, silicon dioxide, germanium oxide, they are acidic in nature. Rather, I would say you should have a tabulated arrangement of various commonly discussed examples of oxides to understand whether it is acidic, whether it is basic, whether it is amphoteric, neutral, like that. So, carbon dioxide, silicon dioxide, germanium oxide, they are acidic in nature, while tin and lead oxides are amphoteric in nature. Whether SnO2 PbO2 or SnO PbO, they are amphoteric in nature. That means monoxide and dioxide of tin and lead, they are amphoteric in nature. While carbon dioxide, silicon dioxide, germanium dioxide, they are acidic in nature, while carbon monoxide is neutral in nature. Carbon monoxide is neutral. Germanium monoxide, that is distinctly acidic. So germanium monoxide and dioxide, they are acidic in nature. Germanium monoxide and dioxide acidic in nature. Tin and lead monoxide and dioxide, they are amphoteric in nature. So a direct catch question can expected from this, or it can be sometimes indirect question. Imagine a long narration type question, where in between getting the hints of identifying the answer, you may be aware of, or you must be aware of the nature of acidic, basic, amphoteric nature of oxides, which will take you to the next step of identifying the answer, where there is a long narrative question where you are able to find the answer step by step informations. So that paragraph is very, very important, I would say. As we are dealing with inorganic chemistry, paragraph by paragraph, point by point, what is quoted in the NCERT should be taken into consideration. We don't know from which part. Rather, if we are dealing with organic chemistry, physical chemistry, inorganic chemistry, questions from inorganic chemistry is very simple, but at the same time risky and difficult also. Why simple? Because direct factual questions. Point is, if you don't know the facts and figures, you are unable to answer. So it is more or less, it is a memorizing chemistry. More you memorize the facts and figures, more easily you've been able to identify the answer. Unlike in physical chemistry, where you need to solve a question, organic chemistry, you need to solve the reactions that is given, identify the product or the characteristics of the reaction. Nothing like this here. Next is reactivity towards water. Reactivity towards water. Carbon, silicon, germanium not affected by water, while tin decomposes in steam, giving SnO2 liberating hydrogen. Carbon, silicon, first 3 members, no reaction. Tin can react with the steam, giving SnO2 and water. Lead is unaffected by water, probably because of protective oxide film formation. Lead is unaffected by water. That is the reason why older days lead pipes were used for the transportation of water. But there was a slight bit of problem. Lead is having a problem, the tendency to slightly dissolve. We call it as plumbosolvency. Plumbosolvency, we know heavy metal contamination in the water is dangerous. That's why we don't use that. Next is the reactivity with halogens. So reactivity with air giving oxides, reactivity with water giving only one reaction we need to go through. Reactivity towards halogens. There are some pretty important points in this paragraph. What are the main points? It gives two types of halides, MX2 and MX4. MX2 type and MX4 type, where X can be fluoride, chloride, bromide. Except carbon, all other directly react with halogen under suitable conditions. Except carbon. Most of the MX4 are covalent in nature, will go for sp3 hybridization and tetrahedral shape. Whether you are taking CCl4, whether you are taking SiCl4, they are all sp3 hybridization and tetrahedral in shape. They make tetrahedral geometry. There are exemptions. What are the exemptions? SnF4 is exemption. PbF4 is exemption. Don't ask for the hybridization of SnF4, PbF4 because they are not covalent. They are rather ionic in nature. So tin tetrafluoride, lead tetrafluoride, it is ionic in nature. No point of talking what is the hybridization for those molecules. Number one. Number two, lead iodide, PbI4 does not exist. PbI4 does not exist. Why PbI4 does not exist? Multiple reasons. One thermodynamic reason is given in the text. Multiple reasons. Number one, lead is not preferring +4 state. Number one. Number two, large iodine atoms surrounding the lead, it is unstable. Number two. Now, what is thermodynamic reason? Thermodynamic reason is nothing but Pb iodine bond formed does not release sufficient energy so that the oxidation character of lead is getting excited and giving more bond with iodine. So lead iodine bond formed does not release sufficient energy to excite the electron of lead and is taking to PbI4 condition. So there is inert pair effect we can take into consideration, large iodine atoms, steric reasons we can take into consideration, thermodynamic reason we can take into consideration. Lead iodine bond formed is not thermodynamically favorable to make subsequent bonds so that ultimately you get PbI4. Right? That is what explained somewhere here in the paragraph which you can go through. Right? We are talking about the halide formation from carbon family. Heavier members, germanium to lead, are able to make halides of the formula MX2. Lead is very much happy to give PbCl2, not PbCl4. Why lead is not happy with the PbCl4? Rather, it is happy to give PbCl2? Inert pair effect. It's happy to give +2 state, not +4 state. +4 state is unstable due to inert pair effect. Okay. Stability of dihalide increases down the group, inert pair effect. PbX2 is more stable than PbX4, while GeX4 is more stable than GeX2. So germanium is on top. It is +4 state more stable than +2 state. As you come down for heavy member, for lead, +2 state is more stable than +4 state. Except CCl4, other tetrachlorides are easily hydrolyzed. Easily hydrolyzed. For example, silicon tetrachloride, it can be easily hydrolyzed. Silicon tetrachloride can be easily hydrolyzed. If you take SiCl4, it can easily hydrolyze. As what happens is, the water molecule is attacking the vacant d orbital of silicon. Water molecule is attacking the vacant d orbital of silicon. So what happens? It is giving you, silicon is able to extend the coordination. Silicon is able to extend the coordination. Now see what is happening. As a bond is formed here, this bond will be weakened and it is breaking. So what do you get? Si. See, this is breaking and is removed as Cl minus. You are getting OH2 plus like this. Now immediately one of this bond will break and the electron will come to oxygen. H will go as H plus. So H plus and Cl minus, HCl out. And what do you get? Si, Cl, 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 OH. This is one step reaction. I repeat, the lone pair of electron with oxygen attack on the vacant d orbital of silicon. And thereby we get such a addition intermediate. Now the chlorine will leave and it is making such a bonding. Here we have chlorine. So one chlorine gone. So in that place OH2 will come. Now Cl minus is out. Immediately from this hydrogen also out as HCl. Now you are getting this. Now this is going to repeat 3 more times. This will be repeated and this chlorine will be removed in the same way by subsequent interaction of oxygen with the silicon. Again 3 times water molecule will interact with the silicon and you can see finally you are getting such a molecule. Some of you may definitely be remembering, this is called silicic acid. You are getting silicic acid. And silicic acid upon heating, this OH and this H will be removed as water. And this OH and this H will be removed as water. You get SiO2, silica, silicon dioxide is obtained. You get silicon dioxide. So this kind of hydrolysis easily happening for other members, but not for carbon. What is the problem with the carbon? What is the problem with the carbon? Suppose in the place of silicon tetrachloride, if we are taking carbon tetrachloride, what is the issue? This is carbon tetrachloride. What is happening here? Why this water molecule can't attack carbon? The matter is very, very simple. In silicon, there is vacant d orbital where the lone pair of oxygen is attacking to make a bond. While in carbon, it is not having vacant d orbital, so it cannot promote hydrolysis easily the way silicon do. Very, very important point. And that is clearly explained in the text also, you can find. It is clearly explained in the text also. This is what I was explaining so far. Okay. Anomalous behavior of carbon. Again, I don't want to repeat again and again the way we were talking about boron. Same thing for carbon. And for every first member, almost similar things are coming. Small anomalous behavior due to small size, due to high electronegativity, due to high ionization enthalpy, and absence of vacant d orbital. Right? These are the reason for anomalous properties of carbon. Already many anomalous behavior we have seen, and one important behavior just now we have seen. Silicon tetrachloride easily been able to hydrolyze, while carbon tetrachloride unable to. And there is one more point which already commented in the previous discussion in group 13 family. Carbon, nitrogen, oxygen. They are able to make stable p-pi bond with themselves and with the neighboring members. Already commented point. And one important point regarding carbon coming is catenation. All of you know what is meant by catenation. Carbon is able to give you Catenation tendency. Carbon is able to perform self-linking ability of carbon is called the catenation. Carbon-carbon bond strength you can find. Enthalpy is 348. It's a reasonably strong single bond is formed between carbon-carbon. So, due to that stable bonding of carbon-carbon, it is able to link by itself, self-linking ability to form long chains, branched chains, cross-linked chains, cyclic molecules. That is the secret behind organic molecules, all of you know. If you take carbon, hydrogen exclusively, hydrocarbons and derivatives, when compared with all rest members of the periodic table, rest all elements together giving periodic table, which we call it as inorganic compounds. A fair comparison will be if the number of inorganic compounds is 1 lakh compounds, if the number of organic compounds is almost more than 10 lakhs. So that kind of high degree of high number of organic molecules are available because of the self-linking ability of carbon, catenation. It is able to give multiple products by linking one carbon to another in the periodic table. The element with the maximum catenation tendency, no doubt, carbon. So that is another point explained here, and this is the order of catenation tendency. This is the order of catenation tendency. Carbon, silicon, germanium, tin almost equal, while lead does not undergo catenation property. Due to the catenation property and stable p-pi bond formation, it is able to show variety of allotropic forms. Carbon shows variety of allotropic forms. A discussion happening on allotropes of carbon. A discussion thereon, allotropes of carbon. There are various allotropic forms of carbon, including crystalline and amorphous varieties. Crystalline and amorphous varieties. Diamond and graphite are two well-known crystalline forms of carbon, and third form, fullerenes, discovered by Harry, Krotos, Malley, etc. A talk on diamond. In diamond, carbon makes a sp3 hybridized dangling type tetrahedral connectivity. That is what we find in diamond. The structural entity might be very much familiar to all. This is carbon, diamond and graphite. One carbon linked to 4 other carbon atoms in space, making a bond angle 154 picometer between carbon-carbon. Diamond, all of you know, the most hard material available, hardest material available naturally, diamond, and is making a dangling type of bond, sp3 hybridized tetrahedral geometry around the central carbon atom. It makes a cubic crystal, diamond. While if you go to graphite, graphite is giving a sheet-like structure. This is sheet 1, sheet 2, sheet 3, and the two sheets are separated at a distance of 340 picometer, and one carbon linked to 3 other carbon atoms in a plane, making sp2 hybridization. sp2 hybridization, carbon-carbon bond length being 141. As sp2 hybridization, naturally the bond length has to decrease. While in diamond, bond length is sp3 hybridization, bond length is 154 picometer. This is graphite, sheet-like structure. And between the two sheets, there are free electrons available. Between the two sheets, there are free electrons available. This is availability of free electrons. And the presence of free electrons make it a good conductor also. Graphite can reasonably conduct electricity, and no doubt many area we are talking about graphite used as electrodes in various electrolysis operation. Number one. Number two, the layers can slide over one another. It is giving a solid lubricating action to graphite. Diamond is extremely hard, while graphite is soft material. Diamond is electrical insulator. Graphite is electrical conductor. This is sp3 tetrahedral. This is sp2 planar hexagonal sheet-like structure. That is what regarding the structural entity of graphite and diamond. All points we have gone through. While the other one is fullerenes. Other one is fullerenes. What is special about fullerenes? Fullerenes are molecular granules. Fullerenes are molecular granules. It is spheroidal molecules. It is spheroidal molecules made by heating graphite in an electric arc in presence of inert gases such as helium, argon. We get a sooty material formed by the condensation of vaporized CN small molecules. It may be C60 normal fullerene, C70, and it can go up to 350 or above. They are the fullerenes are only pure form of carbon because they have smooth structure without any dangling bonds. Others are having dangling bonds. They are cage-like molecules. It has the shape like a soccer ball and is called a Buckminster fullerene, soccer ball structure. The molecular shape is similar to a football structure, where we have some 5-membered ring and 6-membered ring available, 5-membered and 6-membered ring, and two 5-membered ring will never come close. 2 6-membered ring can come in contact. 1 6-membered and 1 5-membered ring can come contact. 2 5-membered rings will never come in contact. It is something like a soccer ball structure. There are 20 6-membered ring and 12 5-membered ring. 20 6-membered ring and 12 5-membered ring. It is maintaining sp2 hybridized system. sp2 hybridized system, and there is free electron localizing across the surface of the molecule, giving aromaticity to the molecule. The free electrons are localized across the surface of the molecule, which turn aromatic character to the molecule. A typical molecule will have 60 vertices, carbon 60. Carbon 60 is a typical fullerene. There are 60 vertices. 20 6-membered ring, 12 5-membered ring, already commented. And we have two different bond length, CC bond length. There are two different bond length, 143.5 picometer one type and 138.53 picometer another type. This is buckyball structure. This is buckyball structure where I can show you the pentagonal ring. This is a pentagonal ring, while this is a hexagonal ring. This is a hexagonal ring. So a pentagonal ring and hexagonal ring can come in contact, and two hexagonal ring can come in contact, but never a pentagonal ring, two pentagonal ring comes in contact. You see, the very next member is hexagonal ring. Here also you have hexagonal ring. Here also you have hexagonal ring. Here also you have hexagonal ring. So around one pentagonal ring you have hexagonal rings. This is pentagonal ring. So around one pentagonal ring you have hexagonal ring. That means two pentagonal rings will never come in contact. That is the speciality of a soccer ball structure. It is known after it was discovered by, as it was commented, Harry, Krotos, Malley, etc., who discovered fullerene molecules. By that time only, there was a very famous architect who actually built a pavilion for a very huge exhibition pavilion, which was actually quite interesting pavilion he constructed, which is for a exhibition, Montreal exhibition. He constructed a pavilion which is similar to the whole entire huge pavilion in the similar shape of a football they have constructed. That was globally attracted construction by those architects. His name is Buckminster Fuller, known after actually as a honor to that architect. the name of the molecule which then discovered, the fullerene molecule, which was quite similar to a soccer ball. As a honor to that architect, it was famous, then called as buckyball structure, Buckminster fullerene. It's named after that architect, Buckminster fullerene. This is the Buckminster fullerene buckyball structure of C60 molecules. There are 60 vertices, 20 6-membered ring and 12 5-membered ring. Another important paragraph comes here. Very, very important paragraph, that is regarding thermodynamic stability of the allotropic forms of carbon. You see, the thermodynamically most stable allotrope is graphite. And delta H formation of graphite is taken as 0. Delta H formation of graphite is taken as 0, while delta H formation of diamond, it is 1.9, and fullerene, it is 38.1 kilojoule per mole respectively, while enthalpy formation of graphite assumed to be 0. While the other forms of non-allotropic amorphous forms of graphite is commended here. What about some important uses of graphite? Let's have a look at some important uses of graphite. Many applications. Embedded in plastic material to form high strength lightweight composite, tennis racket, fishing rod, aircraft cannons. Good conductor, graphite used as electrodes, already commented. Crucibles made from graphite are inerted to dilute acid and alkalis. Activated charcoal used for absorbing poisonous gases, gas mask, used in gas mask. Anything else? Used in air conditioning system to control odor. Carbon black used in black paint. Filler in automobile tires. Coke used as a fuel and energy reducing agent in metallurgy. Diamond is a precious stone, all of us know, and it is measured in carat. 1 carat diamond is 200 milligram. Don't confuse with the carat in gold. For gold, carat means purity. For diamond, carat means weight. 1 carat is 200 milligram. Now a talk on important compounds of carbon family. Important compounds of carbon and silicon. First of all, carbon monoxide. Carbon monoxide obtained by the direct combustion in limited supply of air. Undergoing partial combustion of carbon, we can get carbon monoxide. It is a partial combustion. Or you can get pure CO. We can prepare by the dehydration of formic acid by using concentrated sulfuric acid. Formic acid undergoing dehydration, you can get carbon monoxide. You see, dehydration of formic acid, HCOOH. When heated with the sulfuric acid, you can see water molecule is out and you get carbon monoxide, CO plus H2O. What if it is oxalic acid? Suppose we take oxalic acid. This is oxalic acid. What if it is dehydrated with the concentrated sulfuric acid and heating? It's going to break here. It's going to break here. OH and H out as water. OH and H out as water. You get 1 mole carbon monoxide and 1 mole carbon dioxide. You get equimolar mixture of carbon monoxide and carbon dioxide. So formic acid dehydration, we get pure carbon monoxide. Oxalic acid dehydration, you get equimolar mixture of carbon monoxide and carbon dioxide. And carbon monoxide can also be obtained by treating coke with steam. Water gas preparation, hope you remember. Water gas preparation. Water gas. With the nitrogen, it is called a producer gas. whether water gas or producer gas, they are excellent industrial fuels used for various industrial applications, metallurgical industries, Haber process, various area. We are making use of this combination. It is either water gas, producer gas, carbon monoxide with nitrogen called producer gas, carbon monoxide with hydrogen called water gas, synthesis gas or syn gas. They are good industrial fuels. Regarding carbon monoxide, nothing to comment. It is colorless. It is colorless, odorless, almost water insoluble, and is a poisonous gas. Carbon monoxide is a poisonous gas. Find wide application in metallurgical industry as it is a very good reducing agent. CO can easily be converted to CO2. It undergo easy oxidation. Therefore, it acts as a very good reducing agent. In metallurgy, it is used as a very good reducing agent, carbon monoxide. These are some reducing action. Iron oxide is reduced by carbon monoxide. Zinc oxide is reduced by carbon monoxide. And we know poisonous nature of carbon monoxide is due to in the respiratory system, it creates some difficulties. Carbon monoxide will bind to hemoglobin. Biology students well known about the facts and figures on these characteristics. It binds to hemoglobin, giving carboxyhemoglobin complex, and that affects the service of hemoglobin because the bond is pretty strong. It is almost 25 times stronger compared to the oxyhemoglobin complex. Oh, 300 times. It's almost 300 times. Pretty very high. I was just commenting 25 times. 300 times pretty stronger compared to oxyhemoglobin complex. That means firmly attached, unable to detach. So what happens is the service of hemoglobin may be lost forever and the person will suffer a great degree of suffocation at a higher level of infections, higher level of toxic level of carbon monoxide. The person may become in the coma state, become unconscious, and ultimate cause will be death. Ultimate cause will be death. And a possible antidote we suggest is carbogen treatment. A person affected with the carbon monoxide, due to this lone pair of electron, it is able to bind with the hemoglobin complex. A possible antidote can be carbogen treatment. Carbogen. Carbogen is nothing but CO2 plus O2 mixture. Carbon dioxide oxygen mixture is called a carbogen. A carbogen treatment may be able to help the toxic effect of carbon monoxide. And now the next is a talk on carbon dioxide. A talk on carbon dioxide. Carbon dioxide is prepared by heating carbon, all of us know. Complete combustion of carbon will give you carbon dioxide. Fossil fuel combustion, you get carbon dioxide. In the laboratory, you can get carbon dioxide from calcium carbonate. In the commercial scale, we get it from heating limestone. Commercial production of carbon dioxide. In Solvay process, the carbon dioxide needed for carbonation is obtained from heating limestone. It is colorless, odorless gas. Colorless, odorless gas. Low solubility makes it immense biochemical and geochemical importance. And there is a buffer action. There is a buffer action of carbonic acid and bicarbonate. Carbonic acid and bicarbonate gives the buffer action to the blood. The pH of blood maintained at a level of 2.76 to 2.42. The pH of blood maintained by the buffer action of carbonic acid bicarbonate system. Carbonic acid bicarbonate system. In the environment, Carbon dioxide tolerance limit is 0.03 percentage by volume. 0.03 percentage by volume of carbon dioxide is essentially needed in our environment. It is essentially needed in our environment because carbon dioxide is an essential commodity, essential material needed for photosynthesis, which is the survival system of bio ecosystem. So carbon dioxide is essentially needed. But when the limit of carbon dioxide increases, it causes global warming and other related issues. You see the photosynthesis. Photosynthesis is basically interaction of carbon dioxide and water using green pigment chlorophyll in presence of light producing glucose and liberating oxygen. So by photosynthesis, water is oxidized to get oxygen and the reactant involved is carbon dioxide. By this process, plants make food for themselves, etc., etc. See, unlike CO, it is not poisonous. Unless CO is poisonous gas, carbon dioxide is not poisonous gas. But when the limit of CO2 increases in our environment, that is causing a bad greenhouse effect. Greenhouse effect to a limit is needed. Greenhouse effect, natural greenhouse effect is actually required. It is an energy trapping process. The infrared radiations are trapped in our environment for getting a comfortable living environment. We can't think about the entire energy from the sun hit on our ground and escape back. We can't think about it. It's not a comfortable living environment. Some sort of energy should be trapped in our system. It is done by greenhouse gases and carbon dioxide is the most important greenhouse gas. But when the limit of carbon dioxide exceeds beyond a limit, 0.03% is a natural limit. If it is exceeding from that limit, the energy trapping process will increase and it causes a global temperature to increase, which we call it as global warming. I think many of you heard about dry ice. Dry ice. Solid carbon dioxide is called dry ice. Solid carbon dioxide is called dry ice, also called dry cold, used in refrigeration systems or refrigerant, ice cream, frozen food area. It is very popular. Used for manufacturing of urea. Carbon dioxide, this is carbon dioxide, a linear molecule. Carbon is sp hybridized. Linear system, sp hybridized, and is having two resonating characters. These are the two less important resonating structures of carbon dioxide, less important only, and they maintain carbon oxygen bond length, equal bond length 115 picometer. That is regarding the system carbon dioxide. So carbon monoxide, carbon dioxide. Now a talk on silica. Silicon dioxide, SiO2, silicon dioxide. Silicon dioxide, unlike carbon dioxide is integral molecules. Carbon dioxide is discrete molecules, gaseous state. While SiO2 is not a gaseous state, it is network solid. It is network solid, and this is silicon dioxide character. This is silicon dioxide character. You can see the silica. This is silica. One silicon surrounded by 4 oxygen atoms making a tetrahedral arrangement. Even though it is so given in 3-dimensional arrangement, it is so given in the text. It is not 2-dimensional, it is 3-dimensional network solid, and the surrounding silicon 4 oxygen atoms tetrahedrally bound. It is sp3 hybridized and tetrahedrally bound. The entire crystal may be considered as giant molecule in which 8 membered rings are formed with alternate silicon oxygen atoms. Try to get a 8-membered ring. You see, silicon oxygen. one member. Then next one 2, 3, 4, 5, 6, 7, 8. 8-membered ring. With the silicon and oxygen, it seems like a giant molecule with a 8-membered ring formed by alternate silicon and oxygen. Alternate silicon and oxygen. Ultimately, such an arrangement is possible or done with a silicon at the center position, forming 4 oxygen atoms tetrahedrally, and now this is continuing. That is silica. SiO2. Silica in its normal form is almost non-reactive because of very high SiO bond enthalpy. Resist attack by halogen, dihydrogen, most of the acids and metals at even elevated temperature. However, it can react with hydrofluoric acid, it can react with NaOH. Silica can react with alkali, silica can react with hydrofluoric acid. With HF, it is forming SiF4, and with NaOH, it is forming sodium silicate. A special attention required as silica is otherwise unreactive. It is quite extensively used as piezoelectric material. What is piezoelectric material? A crystal which is subject to get polarization upon giving a mechanical stress. A crystal upon giving a mechanical stress, giving a electrical polarization, and vice versa. That is piezoelectric. Pyroelectric means a polarization created in a crystal upon heating. That is pyroelectric. Used in accurate clock, modern radio, television broadcasting. Silica gel used as drying agent. All of you know. Kiesel gur, amorphous form of silica used in filtration plants. That is about silica. Next is a talk on silicon polymers. You see, various kind of silicon polymers are obtained when alkyl chloride react with silicon. When alkyl chloride RX, when alkyl chloride react with silicon, we are getting multiple products. You will be getting RSiCl3. You can get R2SiCl2. You can get R3SiCl. You can get R4Si. These are different silicon organic products obtained. Monoalkyl silane, monoalkyl silicon chloride, dialkyl silicon chloride, trialkyl silicon chloride, like that. Now, this can give variety of polymers. For example, if we are taking this R2SiCl2, RSiRClCl, if this is hydrolyzed, upon hydrolysis, you will get RSiOHR. See, the 2 chlorine atom gets hydrolyzed to get OH group. Now, this molecule, upon continuous linking with the polymer, imagine this undergo polymerization. Imagine this undergo polymerization. You can get a linear chain polymer. For example, when this molecule is undergoing polymerization, you can see it is getting polymerized like this. It is condensing like this. You see molecule 1, 2, 3 like that. It undergo a condensation over this region. It is going to condense over this region like this. You see H2O out. H2O out, and is getting linked to form OSI, 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 like that. You get linear polymers. linear organosilicon polymers. So R2SiCl2, when hydrolyzed, subsequently undergo polymerization, you get a linear chain polymer. Meanwhile, if you take RSiCl3, look at RSiCl3, RSiCl, see, it is able to give a polymerization. This ground is giving a linear chain, and it can also link like this. It will make a cross-linked polymer. So R2SiCl2, it may give you a linear chain polymer. RSiCl3, it will give you a cross-linked polymer, branched polymer. Meanwhile, R3SiCl, this is used for blocking the chain. The chain length can be controlled, branching can be controlled by R3SiCl. These are some significant point of question from organosilicon polymers. Organosilicon polymers. This is the general formula for organosilicon polymer, R2SiO repeating unit. This is what I was explaining now. R2SiO repeating polymers. Organosilicon polymers, very, very important industrially very famous and very important. Organosilicon polymers. And see the speciality of organosilicon polymers. It is water repelling in nature, high thermal stability, high dielectric strength, and resistant to oxidation and chemicals. They are used in many applications. Surgical cosmetic plants, many surgical cosmetic plants and cosmetic surgery. Cosmetic surgery very famous in the film industry and all. It is a very important material because it is biocompatible. The silicon polymers are many times biocompatible. So it is used for cosmetic surgery. And one last topic is on silicates. Silicates are natural minerals. Silicates are natural minerals containing SiO4 4- anions. SiO4 4- anions. This is the mineral formed with giving silicates. SiO4 4- anion minerals are called silicates. They are represented as Si tetrahedral units. This is silicate unit, SiO4 4-. It is tetrahedral system like this. Or you can understand two-dimensionally, you can represent it like this. Like this. See the 4 oxygen atom, 1, 2, 3, 4, 3 oxygen atom in base and 1 oxygen atom on top, and this silicon is shown with a dot. This is called one silicate. An individual SiO4 4- silicate, that is called orthosilicate. Only one silicate anion, that is called orthosilicate. Only one silicate anion, that is orthosilicate. Sometimes you can find 2 silicates are joined together. You can find 2 silicates are joined together like this. Two silicate units are joined together so that one oxygen atom is shared between the 2 silicates. This is called pyrosilicate. So this is orthosilicate without any sharing. Only one silicate anion. Pyrosilicate means 2 silicate anion joined together. That is pyrosilicate. One oxygen atom is shared. Pyrosilicate. It can be chain silicate. It can be orthosilicate like this. It can be pyrosilicate like this. It can be chain silicate. A chain silicate can be formed like this. a chain silicate. Imagine this forms a chain. Imagine this is framed as a chain. See, it is framed as a chain. Just imagine. See, it is forming like a chain. It is called a chain silicate. It continuously go like this. It is a chain silicate. What is speciality of chain silicate? Here one oxygen atom shared. Here also one oxygen atom shared. Two oxygen atoms are shared. That is chain silicate. Chain silicate. It may be double-stranded chain silicate. A very popular example is asbestos. Asbestos is an example for two-stranded chains, a bi-stranded chain silicate, double-stranded. We call it as pyroxenes. Pyroxenes. Pyroxenes, double-stranded chain silicate. Double-stranded chain silicate. It can be a cyclic silicate. It can be a cyclic silicate. So, orthosilicate, no sharing of oxygen atom. Pyrosilicate, one oxygen atom is shared. Chain silicate, two oxygen atoms are shared. Cyclic silicate, have a look at cyclic silicate. How it forms? Cyclic silicate. See, I have shown 6 members forming a cyclic silicate. This is called a cyclic silicate or ring silicate. Ring silicate or cyclic silicate, where two oxygen atoms are shared. This oxygen atom shared between the two. This oxygen atom shared between the two. Two oxygen atoms are shared. Cyclic silicate or ring silicate. Okay, so orthosilicate, no sharing of oxygen. Pyrosilicate, one oxygen shared. Chain silicate, two oxygen shared. Ring silicate, two oxygen shared. There can be sheet silicate. There can be silicate formed like this. Sheet silicate. It's forming like this. It is getting repeated like this. Sheet silicate. See that? It's getting repeated like this. Sheet silicate. See, it will continue. It will continue like this. Sheet silicate. It goes like this, sheet silicate, where 3 oxygen atom will be shared. 3 oxygen atom will be shared. You see, there is a sharing of oxygen here, sharing of oxygen here, sharing of oxygen here. 3 silicate oxygen atoms are getting shared. It's a sheet-like structure. Sheet silicate. Example, talc. Talc is a sheet silicate. That's why it is having a lubricating action. Talc. Clay. Clay is sheet silicate. So talc, clay, etc. are sheet silicate. Okay. And finally, 3D silicate. 3D silicate means this is one layer. Imagine another layer coming over this. It makes a honeycomb-like structure. It makes a honeycomb-like structure. 3D silicates. Zeolites are example for 3D silicates. Quartz is an example for 3D silicate. So orthosilicate, only one anion, no sharing of oxygen. Pyrosilicate, two silicate joined to make a sharing of one oxygen atom. Chain silicate, double-stranded chain silicate, sheet silicate, 3D silicate. Okay. These are explained over here. And finally, a talk on zeolites. Zeolite is a 3D silicate. zeolite is a 3D silicate. Zeolites. If aluminum atom replace few silicon atom, we get three-dimensional aluminosilicate. Aluminosilicate acquires a negative charge. Cations such as sodium, potassium, calcium balance the negative. That was a previous question. Zeolites are widely used in petrochemical industries, cracking of hydrocarbon, isomerization. ZSM5, a type of zeolite used to convert alcohol directly into gasoline. That was a previous question. Hydrated zeolite used in removal of hardness. Hydrated permuted process, removal of hardness. That is various applications of silicates. And that is the topic P block elements. A reasonably lengthy chapter explaining two different groups, group 13 and group 14. Group 13 boron family, group 14 carbon family. Boron family and the carbon family general characteristics, physical and atomic properties like ionization enthalpy, inert pair effect, various consequences, and a special emphasis on certain compounds. In boron family, borax details, boric acid details, diborane and the details, molecules like borazine, borazole, inorganic benzene, special emphasis, diborane structure, special emphasis. And coming to carbon family, carbon monoxide, carbon dioxide comes under general discussion, silica, silicon polymers, silicates, right? That is what the topic P block elements. So let us conclude the discussion, rapid revision on P block elements. We will meet with another chapter in another class. Till then, bye, see you, take care.